Good morning, everyone. So we continue for the MOSFET, for the introduction for the MOSFET. So last week we have introduced typical CV characteristic. So if right now we look at for the ideal low frequency capacitance, so we'll have the CV curve look like in this way. So we have this is a CV, and as we already discussed last week, actually we have the three regions that will change the different capacitance values. So first of all, once we apply the negative bias, which is our accumulation region, and furthermore, we will start to see the capacitance decrease. So that's related to the depletion. After a certain moment, we can start to foresee the capacitance will increase again. So this is what we usually call as the inversion region. So we all know this is in the case of the accumulation region. So the capacitance is exactly equal to the oxide capacitance. And once we gradually increase the bias, then we start to have this depletion region. This is because our depletions in the P-type substrate is gradually extend to the certain maximum depletion width, and afterwards, once the voltage is high enough, we start to have an inversion. And in reality, we have the two types of inversion region. One is a strong inversion, and also another one is we have the weak inversion. And the boundary between the depletion and inversion, which will be the capacitance will reach the minimum value. So once our capacitance reach to the depletion region reach to the maximum, so that means our depletion capacitance will reach the minimum region. And this is a value, this is voltage we refer to as threshold voltage. And therefore, this is a region for the weak inversion, and this is a region for the strong inversion. And we also have the capacitance here will be equal to our oxide capacitance. And also, one thing want to be noted is that the capacitance here is often we refer to the flat band voltage. So since we have a flat band voltage here, so we have been introduced a concept of flat band voltage in the previous class, and the corresponding capacitance with flat band voltage, that will be the flat band capacitance here. So therefore, this CFB can be shown as here, which is in the voltage at the flat band voltage, the corresponding capacitance is flat band capacitance. So, by the way, this is in the TP type substrate. So if now you have the N-type substrate, the overall situation will be in the reverse way. Okay, so since this is ideal low frequency capacitance, so that means there must be some cases is under the different frequency. So therefore, we have to understand the frequency effects. So there are two sources of electrons that can change the charge density in the inversion layer. The first one is the diffusion of minority carrier electrons from p-type substrate across the space charge region. And the second one is the thermal generation of electron hole pairs with the space charge region. So both of these processes generate electrons at a particular rate here. The electron concentration in the inversion layer cannot change instantaneously. So that means once we under the gate bias here, we apply the AC signal. So the charge here has to respond to this AC signal. But we found out that actually once our frequency goes very high, ideally we should form the inversion charge here. This inversion charge is corresponding to the voltage we apply here, and this is the AC signal, so that will give us additional charge here. So this should be reflect the charge in the inversion layer. But however, once our frequencies goes very high, the problem will be the charge cannot change here instantaneously. So that's how this sentence try to reply here. So in the limit of very high frequency, the inversion layer charge will not respond to a differential change in the capacitance voltage. But we still have to maintain the charge neutrality here, and therefore this additional charge cannot be formed in the inversion layer. Instead, this additional charge will form in this depletion region. So at a high frequency, the differential change in the charge occurs at the metal and the space charge width in the semiconductor, which means this will be reflect at this region. So that's at a high frequency. So again, ideally, once we apply the positive bias, we will start to form the inversion charge at here. So any additional decoupling come from the AC signal should be also reflect the decoupling here. But right now we are in the phase of the high frequency, so the inversion charge cannot reflect, cannot change instantaneously. So that's why the additional decoupling will be formed in the space charge region here, and therefore once we go for high frequency, the CV curve actually will change. So now we can see that our ideal CV, as we have been drawn before, this is a capacitance versus a voltage here. So ideal, we have the so this is our low frequency case. But now we go to high frequency. This is a high frequency case. So that means our capacitance right now is equal to our oxide capacitance plus this additional depletion width capacitance. So the C our inversion capacitance at a high frequency is equal to 1 over Cx plus 1 over CSD here. So therefore, that means at high frequency, our capacitance value is lower because now it's become the series capacitance. High frequency case. So that's very important for the frequency effect in the CV. But I believe that once you understand the reason behind the accumulation, depletion, and inversion, it should be not problem for you to understand the frequency effect, because it's just back to the similar to the depletion case. And there's some additional issues when we talk about CV, and one of the issues is related to the fixed oxide interface charge effect. So that's we need to also understand the fixed oxide interface charge. So the fixed oxide charge effect affects the influence the threshold voltage and flatband voltage. So this is an equation where we have been shown before. So based on this equation, it actually suggests that once our fixed oxide charge QSS prime increase, once we increase the QSS prime, that means our flatband voltage is decreased. So we can expect our CV curve is shift to the left here. So that's effects coming from the fixed oxide charge. So the flatband voltage shift to more negative voltage when we have the positive oxide charge. So therefore, one of the reasons that the CV is very powerful is that it allows us to determine the fixed oxide charge. So the CV characteristic can be used to determine the equilibrium fixed oxide charge. Show me here. So that's why that we often to use the CV to characterize lots of key phenomenon in the semiconductor, because not only to determine the oxide capacitors, also it's useful to determine the fixed oxide charge. And also later on, probably we won't to discuss at this class, but in another class for reliability, we will talk about how to use the CV to determine the interface charge. That's actually one of the main concern for the semiconductor device instability. So in here, just brief to talk about what does interface charge effects mean here. So when we talk about interface charge effect, for sure that we still have to try to understand this by using the Venn diagram. So if you look at the Venn diagram here, so we have the conduction band, we have the valence band. Of course, in middle we have the intrinsic Fermi energy. We have intrinsic Fermi energy, and we already know that there is a state in the semiconductor interface. This is because the periodic nature of the semiconductor is terminated at the interface, so the allowed electron energy level will exist with a forbidden band gap. Then these allowed energy states are referred to as interface states. So as I previously already mentioned that this is our silicon and this is our dielectric. So we all know at this interface is abruptly terminating. So that means this terminating will destruct the latest arrangement in this interface. So in here we don't have the perfect silicon bonding anymore. So once we don't have a silicon bonding anymore, we start to foresee there's lots of interface state can be exist in the forbidden band gap. So this is our forbidden band gap. So ideally we should not have energy and we should not have any allow energy state in the forbidden band gap. And because right now this is terminated place, and that will create a loss of energy state. So we will have the allow electronic energy levels will exist in this forbidden band gap. So this is our allowed electronic energy level. So sometimes we also call this as a state. The reason we call state is because of in the previous lecture we have talked about like a density of state. So these state things also can be used as a here. So that's why we call this as an interface state. So that's a reason. And also we have been also already introduced the upper half one is generally we can call this as an acceptor state. And then the bottom one is we can consider as a donor state. So therefore, once we under the bias, as we know, as a bias is larger enough, we can start to have the electrons formation in this region. And because right now is under the positive gate bias here, so the positive gate bias will start to attract the electron. So we can start to foresee the electron will be attracted towards the left hand side, and therefore it is possible this electron will be start to access this state. Because right now we apply the positive gate bias, and the positive gate bias will start to attract the electrons here, and electron will start to be access this state. And since this is allow energy state, that means this is allow electron that can be filled in this state, and this will become the issue of the electron trapping. Because right now the seat here is available, is empty. So the electron once sees this kind of empty place, so the electron might start to stay in this empty place here. So that will become the trapping effect. So the charge can flow between the semiconductor interface. and this is a trapping effect. And this trapping effect will create a certain reliability issues. Because the electron staying here is not stable. The electron might be stay here for 1 minute and start to go away. The electron might stay here for 5 minutes, for 1 hour, for 10 years to start go away. Depends on the what kind of energy level or what kind of allow energy stay here. So in general, because we cannot determine how long this electron will stay here and how fast this electron will be moving away, so that's becomes one of the instability issues here. So the net charge in this interface is a function position of Fermi level in the band gap. So that's the net charge is here. It depends on the energy level here. So when we talk about reliability, I would say more than 15% of us is trying to understand the trapping, try to understand what kind of bias will lead into the trapping effect and how we can minimize this trapping and how we can do the modeling or we do the lifetime estimations. And also, not only for the electron, with enough negative bias here, we might also to form the holes here. So still the same, once we apply the negative bias here, for sure you will start to form the holes in this side, and the holes will be attractive toward the semiconductor, so we can start to see the holes might start to access this energy state, and that will be being trapping as well. So therefore, we can also expect there's a phenomenon called the hole trapping can be also happen. So in general, we might both have electron and hole trapping happen in the same times here. So that will make our device is very unstable because we cannot predict the IV characteristic. So once we cannot predict IV characteristic, that will give us a problem to further control this device. So the similar drawing has been shown already here. So the upper part is the acceptor state, and then the bottom part is the donor state. So we might start to have electron formation and then start to being trapping here. So acceptor state is existing in the upper half of band gap, and donor state exists in the lower half of the band gap. So that's a basic definition for the acceptor and donor. And acceptor state, this is like the basic definition for the acceptor, which is here. So this is acceptor. So acceptor is basically like the if Fermi level is below the state, so you have an EF here. So we have the EF, we have energy level here. So if the EF is below our energy level, and that is neutral. And once our EF is larger than our energy state, and thus become the negative charge. So if you assume here our energy stay here with the energy level of ET here, so that means this is the case where our EF is smaller than ET, and that's the neutral. still the same if our energy, allowed energy state here is with energy level of ET, and this is a case of EF larger than ET, and that will become this state negatively charged as well. So a donor state is a neutral. So the donor state basically is a completely reverse case, opposite case compared to the acceptor state. So donor state is neutral if the Fermi level is above the state. So this is our ET. So that means if our EF is larger than ET, and that actually exists as a neutral. But right now, if our EF smaller than ET, and that will become the positive charge here. So that's a basic definition for the acceptor state and then the donor state here. And basically, because right now we can see that the whether becomes a positive or a negative charge depends on the Fermi energy, and the Fermi energy depends on our gate voltage. So therefore, the charge for the interface state is then a function of the gate voltage applied across the MOS capacitance. So that means once we apply the different bias, we will start to change this Fermi energy, and that means the different bias will start to trapping, leading to the trapping of this energy state here. So this generally will have the influence on the typical IV characteristic. Just one ideas for your understanding. So once we have ID, VG characteristic. So right now, if our idea is like here, then we have the one threshold voltage. But right now, we consider that there is a negative charge by the acceptor state, and that means we can foresee our IV curve will shift to the right here. This is a case of negative charge in the acceptor state. The original full explanation we can consider is a negative charge in acceptor state, but to simplify this phenomenon, usually we don't always call that the negative charge in acceptor state. This is all very long description, so we can simply refer to this as electron trapping. So this is exactly the case like here. So once we have electron trapping, we can foresee our threshold voltage is increased. And this is because of the once you have the negative charge in the dielectric, and that will become more difficult to form your inversion charge, because you have a negative charge that will try to deplete, will try to repose for your inversion negative charge. That's because mainly due to the Coulomb repulsion, this kind of effect here. And similarly, if we have the positive charge due to the donor state, we can foresee our IV curve will shift to the left here. So this is because this is a positive charge. In the donor state. Or we can just simply consider this as like the whole trapping. So that would be similar to the case like here. So therefore we can start to see our threshold voltage is become negatively shift here. So that's a very typical case we can see from the trapping effect due to the interface state. So in anyhow, this trapping in the interface state give us a problem to precisely determine our IV characteristic, especially to precisely determine our threshold voltage. So that can give us a problem for the further semiconductor applications. So the following just something like another cartoons try to illustrate that when this positive charge can happen. So in this case, this is accumulation. So that means this is a bias in the negative VG here. So we have the positive donors here. So once we have positive donor here, because right now, as you see here, this is exactly in the case our EF is smaller than ET. So this is our ET here. Right now, all of our ET is higher than EF. So that means this is a case of the EF smaller than ET. Then we can start to foresee there's a positive donors here. And once we apply the positive gate bias here, and we can start to see our Fermi energy start to above our interface state, and that will lead to the negative charge here. And this is a case which our EF larger than ET. So we have a positive, we have negative, and the overall, this trapping phenomenon will lead into the stretch of this CV curve. So we can see, if you look at the CV curve here, ideally it should be in this way. But once we consider the interface state, we can start to see this will be shift. There's a certain change the shape for this CV characteristic. Okay, great. So finally, move to the transistor, that the MOSFET that we have been talking for a long time here. But I think the major, like the operation phases has been already gradually explained since the beginning of this class. So I believe right now it should not for you for the first time to understand, but it's kind of like a recap, which is kind of like a summary for all of the MOSFET operation here. So in the MOSFET, we have the different type of structure. The first one is what we call the N-channel enhancement mode MOSFET. And also we have another type called the N-channel depletion mode here. First of all, in most of the cases that we always use N-channel enhancement mode. Try to explain the MOSFET physics and operation, because N-channel enhancement mode is one that we use most often in the reality here. So once we talk about this enhancement mode, it means that this is very simple MOSFET structure. We have a P-type substrate, we have a source and drain, we have a dielectric, we have a gate electrode here. So usually we also have the substrate bias, and in most of the case we will ground the substrate. So we apply the zero bias or ground in the substrate here, and we will start to, the first operation is always we will start to apply the positive gate bias here, and once our positive gate bias is larger than our threshold voltage, that means we start moving the transistor into the inversion region. That means we can expect there's a electron formation in the channel here, and also we will apply the drain bias, and in most of the time the source will be grounded as well. So once you apply the positive drain bias here, so that means this electron will start to attract it toward the right and flow out from the drain side here. So therefore we can expect there's an electron flow from the source to the drain. So that's our electron flow. So that's our electron current. But you also already knew that the current, the definition of current is considers the whole current, which is reverse direction for the electron current. So therefore the real current flow is from drain to the source here. So that's our current flow. So that is already almost like to explain more than 80% of the MOSFET operation. And based on this explanation, we can expect our MOSFET has an IV characteristic shown here. So we have a drain, because what we care now is a drain current. This is our drain current here, versus our gate bias here. So we are interested in the drain current versus the gate bias, and right now we can foresee in the beginning it should have no current. The current will be only half once our gate voltage is larger than threshold voltage. So this is our threshold voltage. So that means once our gate bias is larger than threshold voltage, we can start to foresee the current is increased here. So in here we define this kind of a transistor where our threshold voltage is larger than 0, and that's why we call this as an enhancement mode. What does mean enhancement? Enhancement, it means that we increase, we do something to enhance the current. We do something to enhance the carrier density. So what we are doing here, we increase our gate bias to enhance the current density. So that's why in here we call this as an enhancement mode MOSFET. And on the other hand, we also have the one that what we call as a depletion mode. It's shown me here. Depletion mode is actually another operation, but from this device schematic, there's a one thing difference is you can see the blue one here. Blue one is the channel, so that means the channel here is already existed even we don't apply any bias. and that means the electrons already can flow in the channel here. But right now, what we have to concern is how can we turn off the device? So if you look at the IDVG characteristic, the channel is already there in the beginning. So that means even we apply the VG equal to 0 volt, there's already the current flow here because the channel is already there, even we don't apply any bias. And then now the concern is that how do we turn off the device? So if we want to turn off the device, what we need to do is apply the negative bias here. So after a certain moment, we still can turn off the device, and this still defined as a threshold voltage, and therefore the depletion mode means that our VTH is negative, is smaller than 0, and we need to apply a minus VG is needed to turn off the channel. To turn off the channel here. So we need to apply negative bias, and negative bias will start to form the depletion region. So once we have a depletion region, the electron here cannot flow anymore because all these electrons will be depleted, and that means we don't have the electrons in the channel. So that's why we call this as a depletion mode. So in this case, we need to apply the negative bias is needed to deplete the electron channel, and that's how we are able to turn off the transistor here. And that's why, because we need to apply the negative bias to deplete. So that's why we call this as a depletion mode. We call this as a depletion mode. So in general, the only difference between the enhancement mode or depletion mode from the electrical characteristic, that's the main difference are the threshold voltage. The enhancement mode, we have the positive threshold voltage, and the depletion mode, we have the negative threshold voltage. In the MOSFET, it is not very often to use as a depletion mode. So the enhancement mode is a main architecture or main device we use in the reality. But however, in certain spatial technology, especially related to the 3-5, like the case of gallium nitride, is very often to have a depletion mode characteristic. This is because the channel is already formed in the beginning, even there's no any additional gate bias. Okay, so this is a typical circuit symbol for the MOSFET. So we can draw in this way in the circuit design that we don't have to always to show these things. We can simply draw in this way, and people will understand this is a MOSFET. So we have a gate, a drain, source. We have the substrate body here, and this is a case for the depletion mode. Okay, so on the other hand, we can also consider that not only for the N-channel enhancement mode, they could be possible to have the P-channel enhancement mode as well. So similarly, if you consider the p-channel enhancement mode here, the only thing is different, which will be now we consider as a N substrate here. And if right now we consider the N substrate here, how do we form the inversion layer here? In here, we need to apply the negative gate bias. So the negative gate bias will start to form the whole inversion layer, which is so therefore we can start to form the holes in the channel here, and therefore we can start to expect the similar IDVG characteristic. So we can start to expect the similar IDVG characteristic. The only thing different is right now we apply the negative gate bias. So in the beginning we have a negative gate bias, and once we have enough negative gate bias, we start to form the whole current here. So that's our typical IDVG for the enhancement mode p-channel MOSFET here. And also because right now we apply the enough negative gate bias to enhance the channel. The channel is not layer in the beginning, so we still call this as an enhancement. And in reality, also the p-channel enhancement MOSFET is the one that we use most often. So in the later on, whenever we talk about the P MOSFET, we always consider the enhancement mode as the first priority. Of course, there's still one called the depletion mode. Similar to the N-channel depletion mode, the P-channel depletion mode, we have the channel already formed under the gate dielectric here. So we already have the channel here, and therefore what we do now try to turn off our device. So this means that at the 0 volt here, the channel is already there and the current is already there. But right now what we need to do is try to switch off the channel, try to deplete the channel. So now we have to apply the positive bias. And once we apply enough positive bias here, then we can start to turn off our device here. And the reason why we need to apply the positive bias is because right now we already have a lot of the positive charge, which are the holes there. So we need to positive bias is needed to turn off the channel. So that's why we need to start to apply the positive bias, and once the positive bias is positive enough, is high enough, then current will back to the 0. So that's why we consider this one as a depletion mode device. So I think the operation, no matter for the enhancement mode or depletion mode, no matter for the N channel, P channel, actually the operation are very similar. So just have to take the patience, try to understand once. If you understand once, I think you will not forget it. Okay, so we have been already talking about for a while that how the current formation, how the typical IDVG look like in the MOSFET. But right now we have to spend the time in very details. So let's use an N-channel enhancement MOSFET with a gate source voltage that is less than the threshold voltage, and then with only a small drain to source voltage. So right now you have to remember that the MOSFET is a 3-terminal device. So that means we always have to consider every aspect with all these 3 terminals. And fortunately, we always prefer to ground it, the source, put it as a 0. And we always prefer to ground it in the substrate. The MOSFET is 3-terminal, but sometimes we can consider the 4-terminal as well, because you can also apply the bias from the body, from substrate side. So, but in most of the cases, we will always try to connect this and to the grounding. And therefore, what we need to concern here is only the impact comes from the gate and the drain bias. So in the first stage, we consider the case where our VG is smaller than our threshold voltage. Our VGS is smaller than threshold voltage. And also right now, we consider the case with a very small VDS here. This is how this sentence means that we consider VGS is smaller than threshold voltage and with only very small VDS. And the source and substrate or body terminal are at the ground potential. So with this bias configuration, there's no electron. There's no electron inversion layer. So in here we don't have the electron inversion layer, because right now our VG is smaller than VTH. But right now we have to also notice that the drain to substrate, there's a PN junction here. Right now we apply a small VDS. Actually, we try to reverse bias of this PN junction. So right now, this PN junction is under the reverse bias. So that's the first step here. We apply the VG smaller the threshold voltage, so we can expect that there's no electron formation in under the gate region. But in the meantime, because of there's a slightly reverse bias in the PN junction in the drain side, so we also can expect that this is under the reverse bias. That means there's no current flow. So in general, the drain current is equal to 0 at this case. And so the next step is will be interesting to gradually increase our threshold voltage. So right now, if our VGS is larger than threshold voltage, so once we apply the VGS larger than threshold voltage, we can expect less electron inversion layer here. So that's here. So we can start to have the electron inversion under the gate region. This is because our gate bias is larger than threshold voltage here. So right now, we also still apply the positive VDS. So you have the negative charge here. you have the positive bias here. So therefore, the electrons can start to flow from left to the right. So that's our electron flow. So once we apply the gate bias larger than threshold voltage, we have an electron inversion layer has been created, so that when a small drain voltage applied, the electron in the inversion layer will flow from the source to the positive drain terminal here. So that's the second step here. And just reminder that right now we consider the ideal case that there's no current flow in this gate oxide region, because we assume there's no any electron tunneling, there's no quantum tunneling, there's no any gate current. But of course, in reality, this is not true. But right now, we try to simplify the case. So, under this case, actually, for small VDS, the channel region has a characteristic like a resistor. So that means our drain current right now can be considered as a linear proportional to our drain bias, which has a factor here, GD, and that's what we call as a channel conductance. And this channel conductance is 1 over resistance. So that's a 1 over resistance. So this is because of at this moment that we apply only small drain bias, so we expect that the drain bias didn't influence our channel charge, didn't influence our inversion layer. So right now, if you consider the MOSFET schematic here, we have the source, we have a drain here, we have a dielectric and gate metal. And if you consider the two cases, first one is a VGS larger than threshold voltage, so for sure we can expect the channel formation under the gate. But if VGS is much larger than threshold voltage here, then so right now is a VGS much larger than threshold voltage, and this is the source drain. So our channel, because right now we can expect a higher electron density, so our channel will become thicker here. So the thicker of the channel, that means it's a low resistance. So the drain current versus this should be the IDVDS. So now we consider the drain current versus drain voltage, IDVDS, and then our current is linear proportional to our drain bias, as shown me here. So this is a linear proportional. But as we increase the gate bias, actually we will have the large electron density. So we can also consider this is a VGS1 larger than V2, and this is a VGS2 larger than VGS1, and this is VGS3 larger than VGS2. Because a higher gate bias, we can have a large electron inversion charge in the channel as shown in here. So that's why you will see increase the gate bias. You also start to see the increase of the current here. So inversion layer is a function of gate voltage. Therefore, the basic MOS transistor action is a modulation of channel conductance by the gate voltage. So this sentence actually just reflects the understanding of this one. The modulation of the channel depends on also the function of our gate bias. So once we apply the higher gate bias, we can expect the higher electron density in the channel here. So if you look closely for this equation, so the mu1 here is the mobility of the electron in the inversion layer, and Q1 is the magnitude of the electron layer charge per unit area here. So that means if you have a higher charge in the channel, then that will also increase your channel conductance. Okay, so this is only under the case of the small VDS. So you still have to remember that we are considered simultaneously to change the gate bias and drain bias, but now we assume the drain bias is very small and only the gate bias influence is discussed here. But next step is right now. This is just a recap of what we have been shown. This is when our VGS larger than threshold voltage, and also the applied VDS is small. The applied VDS is small. So right now, because the applied VDS is small, basically the channel here is only depends on our gate bias here, but we still have a small drain bias here, so we can start to have the electron flow from left to the right, and that means our current flow is from right to the left. And right now is only the linear dependency between the drain and also the VDS here. But the next stage that we will be interested in if we keep increasing the VDS, because right now this is ID VDS, we only consider this region. But how about if our VDS is increased? So when VDS value is increased, the only things will change is the voltage drop across R side near the drain terminal decrease. And this is because if you consider the voltage difference between the gate and drain side, this is what we consider as a VGD. VGD is equal to the VDS, VGS minus VDS. But right now, if we increase VDS, and for sure our VGD is decreased, and once the VGD decrease, that means the channel, the electron concentration in the drain region, in the closed drain region, will decrease as well. Therefore, the inversion charge decrease. In the place which is near the drain terminal. So we all know our conductance is only related to the inversion charge. But right now, we can see this part of the inversion charge is actually decreased. So that means the conduction for the conductance, which will decrease the conductance here. This one, the channel conductance will decrease, because in the beginning it should be very uniform. But right now, if we keep increase the VDS, we can see the decrease of the channel, decrease of the inversion charge here. So expect the conductance will decrease. And therefore, if we start to look again for the IDVD curve, original, we have linear dependency of a VDS. But right now, as the VDS is start to getting higher, then the channel conductance decrease. The channel conductance decrease, that means the slope will decrease as well. So the slope decrease. The slope decrease is because our conductance decrease. So now we can foresee, right now we don't talk about any equation yet. For sure later we will still have to spend the time to derive the equation, but the equation is not the point. The equation just allows to further prove our guess. Right now we are still in the phase of the physics-based guess, physics-based understanding here. So we can foresee that once we increase the VDS, actually our drain current will start to slightly saturated. So when VDS value increase, the voltage drop across the oxide near the drain terminal decreases, which means the induced inversion charge density near the drain also decreases. So therefore, the incremental conductance of a channel at the drain decreases, which then means the slope of the IDVD will decrease. So the slope here is here. So that's why based on this physics understanding, we can expect that once you increase the drain bias, the current cannot increase very fast anymore, and then the slope will start to slightly decrease here. The voltage drop across the oxide near the drain terminal decrease. This is here. Okay, so great. Then for sure that we will be interested to continue to increase our VDS and see what happens. So right now, if we further increase our VDS, we can start to expect the channel here will be decreased as well. And in the end, there's a possibility that the induced inversion charge density becomes 0 at the drain terminal. So when VDS increases to the point where the potential drop across the oxide at the drain terminal is equal to VT. So right now, if voltage drop here is equal to VT, and that means actually this inversion charge here is become 0. And therefore we consider this is a point where we call as a saturation. So we often call this this is right now we consider this is a current start to showing the saturation characteristic. Why we have a saturation? This is because now our ID VDS, so as previously shown in the beginning, is a linear increase, but then the slope is decreased. And after a certain moment, the slope will become as a flat here. This is because right now the inversion layer near the drain terminal is equal to 0 at this moment, and therefore we define this one as a VDS set, because afterwards we have the current as showing flat here, and we consider right now the device transistor is operated in the saturation region. So that's why we call this as a VDS set here. So, but we still will be interested in that if we further increase the VDS when the VDS is larger than VDS set, and what will be the possible the channel look like at this moment. And when VDS become larger than VDS set, the point in the channel which inversion charge is just 0 moves towards the source terminal. So that means so this is our interface between the oxide and the channel semiconductor right now. Because our VDS is much larger than VDS set here, this will lead to the channel formation look like here. This is a point which inversion charge at 0, and this one will start to move towards the source side. So in this case, electron enter the channel at the source. So still the same, electrons can move into the channel here, travel through a channel toward the drain, and then the point where the charge goes to 0. When the charge moves to here, the charge will find out that there's no channel anymore. But the problem is that how this electron can still move to the drain side. This is because there is an electrical field here. And this electric field will help this charge start to move toward the drain side here. In this case, electron enter the channel and the source travels through the channel toward the drain. And then at the point where the charge goes to 0, the electrons are injected into the space charge region, where they are swept by the E field. To the drain contact here. So first of all, this is our 0 here toward the source, and the next is the lesser region where we have the space charge region. So now we have to understand why there's a space charge region in the drain side. So again, if you try to plot the full schematic for the source and drain and gate, so right now the VD is larger than VD set here, and you have still remember this is a p-type substrate and this is a N+. So right now the VDS is high. The VDS high, that means the depletion region in this PN junction is actually get extended. So we will have very obvious depletion region in this drain and substrate PN junction right now. And this is why the text called there's a space charge region here. So we will have a large space charge region between the drain and substrate PN junction. And also, you all already knew that inside the space charge region, we will have the electric field. So the electric field will be in this direction. E field will be in this direction. And again, the channel is formed like in this way. So therefore, our electrons from source start to move toward the channel and then will be swept by the electric field. In the end, the electron can start to enter the drain side here. So that's why the text is described as shown me here. And this is because for this part. So this is one of the reasons why we typically call this as a field effective transistor, because we need to have a certain electric field to help the carrier, to help the electron flow from the source to drain side. So that's a field effective transistor here. So now if you try to look at the ID-VD curve, ID-VDS, so we already know in the beginning we have the linear region, and after a certain moment we start to see this will be saturated into the point where we have the VDS set here, and then the channel will be look like in the beginning is with a small VDS, so the channel is uniform and only depend on the gate bias. But once we increase the drain, we can see the channel is start to change, and that's why the slope is decreased. And at this point where we have the zero inversion charge in the drain side, because right now the VDS is equal to threshold voltage, and after this point we start to see the channel charge is become like here, and therefore the charge movement here can, which is influenced by the electric field in the drain and substrate PN junction here. And normally we call this as a saturation region. This is because right now the current is saturated, and the region where we have the linear dependency of the gate voltage is a region we call the linear region. Okay, so finally we complete the picture for the IDVD characteristic for one MOSFET. Right now it's still based on the physics point of view, so we don't have any very hardcore equation now, but right now we already can expect what the IDVDS look like. And then the next slide we'll start to consider how to derive the IDVD characteristic here. Okay, so we will take a break and then we'll come back at the 11.
有写6月10号要考期末，可6月10号好像是端午节。
哦，可能到时候还会改，我因为那时候可能没有考虑到。对，但是
会再延还是会改到这样子？
我可能会尽量在那个礼拜，但是可能会那个礼拜的再挑，可能也会再挑个晚上时间。对，到时候可能，下礼拜或下礼拜会再公布一下。好。Okay. Now we will start to do some of the equation calculation, try to prove our physics-based guess for our IDVD characteristic. First, just want to show the summary for the equation that we can use for the linear and the saturation region. So some of the in the textbook we call the non-saturation region, but actually it's more often we call as a linear region. So the linear region, the current equation is shown. The drain current is equal to gate width, mobility, and oxide capacitance over channel length 2L. And also it depends on our gate and the drain bias, so which is written here: VGS minus VT, VDS minus VDS squared. So that's the equation for linear region. And the equation for saturation region is shown in here. Still the same, is dependent with the gate width, mobility, Cx, 2L, and VGS minus VT as shown in here. And if we try to plot the IDVD characteristic, this is IDVDS here. So the full curve for the linear and then saturation region is shown me here. and this is VDS set is here. So this is a V is equal to VDSS equal to VGS minus VT. And in the left hand side is a linear region. In the right hand side is a saturation region. And this is IDVD with different VGS. So this IDVD has been already shown in the last slide. So now we are plotting the full IDV sets with all different kind of VGS, and also with a clearly indication the region where we call the linear region and the region where we call the saturation region. So now we will have to start to derive the mathematical equations shown here. So, and therefore we have some assumptions. The first one, the current in the channel is due to the drift rather than diffusion. And there's no current through the gate oxide. A gradual channel approximation is used, which, as shown here, this approximation means that the EX is essentially a constant. Any fixed oxide charge is an equilibrium charge density at the oxide semiconductor interface. The carrier mobility in the channel is constant as well. So these are the assumptions that we use to derive the current voltage equation. So we're starting from the basic. The first one from the Ohm's law, we all know the current is equal to, it's a linear dependent on our electric field. So as shown me here, so that's a basic equation here. And you can look at this schematic. There are the two very important dimensions we have to know. The first one is a W. So W is a channel width. And another important dimension is L. L is a channel length. So we have the W and L as shown in here. And first, we still have to back to the charge neutrality here. So based on this is a charge distribution in the N-channel enhancement mode at the case where threshold gate voltage larger than threshold voltage here. So we have the charge in the gate side, we have the fixed oxide charge, we have the inversion charge, we have the depletion region charge. So these four kinds of charge will be equal to 0. That's because due to the charge neutrality here. And based on the Gauss law, we have this kind of equation, and where QT is the total charge enclosed by the surface, and En is a outward directed normal component of electric field across the surface. And also, if you look at this schematic, surface 4 is the only surface that contributes. So therefore, we can start to have this equation is equal to QT, and where QT can consider as this one as well. So again, this is also another Venn diagram we use, and then so our Fermi energy EFP minus EFM, that's the Fermi energy in the metal side, will be equal to bias as shown here, and therefore we can further consider VGS minus Vx will be equal to this term, and therefore our VGS minus Vx is equal to Vox plus 2 phi Fp plus phi Ns, and where phi n is a metal semiconductor work function difference, and phi s equal to 2π for the inversion condition. And right now, our electric field in the oxide just simply can be calculated by the voltage over oxide thickness. So therefore, this we can have this bunch of equation, and then we can also consider this one is where we have to use the current, and finally we can have this equation out here. So once we do the current, we have to integrate between 0 to the channel length in the x direction of current dx, which will be equal to this one. And right now we consider the drain current is equal to minus Ix here, when VGS larger than VT and VDS is smaller than VD set here. So finally we can have this equation. So that's our equation for the linear region as shown here. And the value VDS at the peak is when this derivative over VDS equal to 0, and therefore we can start to have this where this is a VDS set at here. And because right now we all know that after this region we will reach to the saturation. So this is our saturation part. So when VDS larger than VDS set, we can start to use this one to get this one, and in the end will become to this for the drain current in the saturation region. So this is the equation in the saturation region, and this is equation in the linear region. So that's a mathematical calculation for this equation. And furthermore, we back to this equation. When we consider very small VDS, this equation can be recalculated as shown here, and therefore we have this correlation, and this correlation allows us to calculate this slope, which also will be equal to this one. So the extrapolation of straight line to 0 current give us a threshold voltage and the slope is proportional to the inversion carrier mobility. So basically, if we try to plot in this versus this, then from the slope, from these intersections, we can have the threshold voltage. From this slope, we are be able to calculate the mobility. So similarly, if we try to consider the p-channel device, we have exactly the same equation. The drain current is equal to, but now we have to consider the whole mobility here, because now it's a p-channel, but the rest, the things are the same. And also we have to consider the VSG now. So now it's a VSG and VSD. And also the ID set is the same. So the following is one very simple example how to derive the current here. So this is a normal question, not only for the course exam, it's also the question in the reality case in the semiconductor world that we have to design the certain parameters that intend to reach our target current. So this question is design the width of MOSFET such a specific current is induced for given applied bias. And we consider ideal N-channel MOSFET with a parameter of the channel length 1.25 micrometer. Mobility is equal to here. CR is equal to here, and then this is threshold voltage here. So we have to design the channel width such that the ID set is equal to 4 milliamp. At the VGS equal to 5 volt here. So the calculation here is very simple. We just try to use the ID set equation is equal to so now our goal is to achieve 4 milliamp in the saturation current, and we just put everything we know in this equation. So the channel length is 1.25 micrometer, and mobility is 650, and CR is 6.9 10 to minus 8, and this is the requirement is at 5 volt and threshold voltage is 0.5 volt here. So by consider this equation, we can have the width is equal to this value, and this give us a certain design that how we can make our transistor to achieve such current level that we need to design how large of a gate width here. So in the previous schematic, we only show the two-dimensional cross-section, which is this one, the source and drain here. And only show the gate. But in reality, when we design the transistor, actually we have to design in the three-dimensional way. So that means actually our transistor should also have to consider the width. So right now in this question is already provide the length, which is 1.25 micrometer, and the question is that what is this width? So in this requirement, we have to design the transistor with around like a 12 micrometer. But in reality, when you try to fabricate device, you have to design usually the structure or the how we actually decide the geometry or dimension in this transistor, and usually we consider that term is usually called as a layout. And then layout is only the design that you look from the top view. You look from here. So if you look from top here, you can find out that when you draw this your transistor in the layout design, it will only look like in this way, because we only see the gate pad on top, and this is the W you need to design here, and this is the layout of this gate side gate pad here. And for sure that if you look at top view, you are not only see the gate, you also will see the source and drain. So we also will have the source and drain pad. Source and drain here from if you look at from the top view. And this is our gate pad. So this is a very simple design question that we have in reality, that we need to determine a certain size of our transistor in order to reach our current target. Okay, so now we have to move something else in the MOSFET here. So the MOSFET is there's one very important parameter what we consider is called transconductance. So transconductance is defined as a change in the drain current with respect to the corresponding change in the gate voltage. So that means the transconductance here, Gm, is equal to the change in the drain current over the change in the gate voltage. So that means this is the equation, the derivative of the drain current versus the gate voltage here. So that's the definition for the transconductance here. So now if you look at for the IDVG curve, and we have IDVG similar like in this way. This is our typical IDVG characteristic. But now if you plot as a transconductance, versus VG, so basically you will see the curve like in this way. So that's the derivative, the drain current versus a gate voltage. And the important thing for the transconductor is to describe that how much the current gain with respect to the gate voltage. So that's why sometimes consider as a transistor gain as well. And we can not only understand the transconductance from this curve, but also from the typical IDVD. We can also understand the transconductance. So if you look at the ID versus the VD here, so as you know, now we have this kind of IDVD curve. So the transconductance is exactly equal to, so assume we have the current ID0, ID1, ID2, ID3 here. And also each ID is corresponding to one VG0, VG1, VG2, and VG3. Therefore, the transconductance actually just this difference, right? Because the transconductance, by definition, GN1 is equal to your ID1 minus ID0 over VG1 minus VG0. Therefore, that's why that we consider the transconductance as a transistor gain or current gain, because the transconductance is actually evaluate the difference of the current level when we increase our VG. So this is a bias of a VG here. So if we have the curve like here, what does it mean? What does this mean? That actually if we try to apply a very large gate voltage, then actually our current gain is decreased. So we can foresee once we increase our gate voltage, but now the difference between these two are getting smaller and smaller. This is because right now the gain is decreased. So now if we try to have this one, ideally hope this is always larger as a larger possible if this is a linear increase of the current gain. But the problem is that after this peak, the gain is decreased. That means this difference is decreased. So this GN decrease is exactly reflect the issue here. So one of the transistor design or fabrication targets, we want to have linear increase of gain. So ideally, if we can make the transistor that have the GM versus VG is shown in this way, that's perfect. That means the gain here is even higher and higher. But however, it's not possible. It's always after reach this peak, you will start to decrease. So our goal is trying to extend this period as larger as possible. So that's sometimes is one of the goal that we have achieved during the semiconductor device design or fabrication. So that's why the transconductor is referred to as a transistor gain, because we are consider this part as a gain. In the non-saturation region, we can just simply put all the equation we already have here, then we can have this, which is equal to here. And in the saturation region, we can have here. Okay, so that's related to transconductor. And next one, we have to start to talk about substrate bias effect. And sometimes we also call this as a body effect. In the previous calculation or understanding, we always assume our substrate and the source are all grounded. But there's a chance that our substrate bias is not equal to 0. So when VSB larger than 0, the service will try to invert when phi s equal to 25p. However, these electrons at a higher potential energy than other electrons in the source, the newly created electron will move laterally and flow out of the source terminal here. So in general, is that if we only consider the service potential influenced by the gate, so ES is equal to 25Fp. But right now, we also have to consider the impact come from the substrate side. So therefore, our service potential is changed. E phi s will be equal to E 25Fp, but right now we have to consider impact come from the substrate. So that's the only thing we have to worry, because right now we have a different substrate bias, and different substrate bias will influence our service potential. And because of this different substrate bias influence our service potential, so once we consider all the previous calculation, we need to also incorporate this VSB now. So because in the previous one we have 25p, and now we have to consider VSB. So therefore, there is a difference between the threshold voltage influenced by the VSB here. So that means once we apply the substrate bias, that will change our threshold voltage. This is because our service potential is also changed as well. And in here we define this as a body effect coefficient, and therefore delta threshold voltage here is equal to this one. So that's all. So actually the overall influence from the body effect just will slightly start to change our threshold voltage. So we have to consider that's actually influence. So in here, just in the end, to calculate how the threshold voltage can be influenced by our substrate bias here. So finally, we move to the last one, that one of the key important things for the MOSFET is that in the end we have to integrate the PMOS and NMOS and become what we call complementary MOS, or sometimes we just refer to as a CMOS. So basically, CMOS just a combination of the PMOS plus NMOS. So in the left hand side, we have this is NMOS, and this is a PMOS. Or we can also fabricate in this way, NMOS, PMOS, and this is NMOS, PMOS. So in here we won't introduce the detail of how this NMOS, PMOS can be simultaneously fabricated in the same process, but I think once you follow the semiconductor process class, you should have some knowledge will be lecture later regarding to the fabrication for the CMOS technology. But the most important thing for CMOS is to realize the inverter. So in the upper part we have a PMOS, in the under part, in the below we have the NMOS, and we usually collect the gate together, that's a V in. We collect the out together, that's a V out here. And the main function for the CMOS is to realize the inverter. So that means if we apply the signal, if we have a digital signal as a 1, it will give us a result of a 0. If an input signal as a 0, it will give us a output signal as a 1. So that's the main function we needed for this inverter. So the next slide just some more detail on how this CMOS inverter operation. So as you already see in the previous slide, we have this so the upper part is a PMOS. The bottom part is a MOSFET here. So as you know, we have always, this is a gate, this is a source, this is a drain, this is a gate, this is a drain, this is a source. And in here we will connect it as a grounded. In here we connect it as a voltage. That's we often call this as a VDD here. And how this CMOS is operated is that the first one, if you consider this part here, if our V-in is larger than threshold voltage here, so this transistor will turn on. This transistor will turn on, we will start to have the current flow here. And once we have a current flow here, and that means that we actually will connect the Vout equal to this ground signal. So that means this is our V-in, this is our Vout here. In the beginning, if we have the V-in as this kind of a waveform, and this is a V-in is a high voltage, so it must be larger than threshold voltage here. But the one this is high, and actually our output voltage will be not exactly, but it will be the similar to the ground voltage. That will be equal to almost approach to the 0 here. So therefore, in this case, we will have the lower voltage in the output side. So that's why we consider this as a 0 here. So once the first step is that the V-in is larger than V-in is applied larger than VG threshold voltage in the N MOSFET here. Then the N MOSFET will turn on. And therefore, the VR will approach to the V ground. So therefore, we can consider this is a input signal, so 1, and this one will be input signal as the 0 here. So that's why you will see this is 1 and this is a 0. And next one is once we as a 0, and then we start to have this high, because right now the PMOS is operate, so your VR will try to approach to the voltage similar to the VDD here. So now you have a high voltage. So once we have a bunch of the waveform in this way, then we can have the inverter is opposite signal as a V. So that's why we consider this as an inverter. So that's how this CMOS operations. And finally, just share some of the advanced, also the recent study that how we actually further to fabricate the advanced transistor to prove that there's no scaling issues here. So this paper is published in the Nature couple years ago. It's trying to demonstrate the MOS2, which is a two-dimensional material transistor with a 1 nanometer gate length here. So first of all, we can try to look at together on the abstract. So the abstract is saying that scaling of silicon transistors is predicted to fail below 5 nanometer gate length because of several, especially very severe short channel effect. As an alternative to silicon, certain layer semiconductors are attractive for their atomic uniformity thickness down to a mono layer, and lower dielectric constant and large band gap, and then heavy carrier effective mass here. And these are just a general introduction. As I say, this is mainly to talk about the background information. To describe that why these people were working on this project, working on this topic, because of there's some issues that the silicon transistor cannot downscaling below 5 nanometer here. And in here, this is a key point. Here we demonstrate the MOS2 transistor with a 1 nanometer physical gate length using single carbon nanotube as a gate electrodes here. So that's the key information. That's the key object for this paper. They want to demonstrate that the transistor can be functional, even has a 1 nanometer physical gate length here. This ultra short device exhibits excellent switching characteristic with near ideal substrate swing. Of the 65 millivolts. So now you see that in the couple of the lecture before, we already mentioned to you that the concept of the substrate swing, that we have already foreseen that the substrate swing is one of the key concerns for the advanced semiconductor transistor. And the target for this paper is they also try to demonstrate the device with a very good substrate swing. It's a 65 millivolt per decade, and also the on-off ratio is larger than 10⁶ here. And simulations show affected channel length of the 3.5 nanometer in the off state, and also the 1 nanometer in the on state here. So now I believe that if you already look back for this class, you probably can already have the basic understanding of this literature, because whatever they say, the only things we don't know so far is just this material. There's a material called MOS2, but the rest of the concept is already discussed in this lecture here. So if we try to summarize here, the topic is they try to fabricate a transistor with 1 nanometer gate length. If you don't understand the MOS2 is fine. I also didn't understand very well for MOS2, but it doesn't matter. It's just a kind of material that they try to demonstrate in the end to achieve the transistor with only 1 nanometer gate length here. And the result indicates that they can achieve the substrate slope of the 65 millivolt per decade. And also the on-off ratio is 10⁶. So that means the result here should show, right now if we don't look at any figure so far, but we can already guess what kind of information in this literature. So if you look at the drain current versus the gate voltage here, and right now you try to plot as a log ID here. So we all know if we try to plot log ID, the curve will look like this way. And the result for this paper should show this is off. This is on. So the ratio between off and on is 10⁶. And also the substrate swing is 65 millivolt per decade. So that's actually the main point for this literature. So I believe so far we don't look very detailed. We don't look at any figure. We don't look at any equation. We even don't know how to they fabricate this, but we already know the conclusions. And of course, we can look at this is abstract, and this is introduction for this paper. It's very long description, but we don't have to read everything. So first keyword we have to find out is however. So they say, however, large-scale processing and manufacturing of Tian-Li device down to such small gate lengths are existing challenging, requiring the further innovation. So they say that if you try to fabricate this Tian-Li based device, it requires some of the innovation. And finally, this is key. They found a way fabrication of electron at such a small scale length over large area requires some advance in the lithography techniques here. And nevertheless, he used a certain way to overcome these issues here. So these are some key transition word or key summary word that give us a hint that after these words we should pay attention, because usually after this word the key points is coming. Okay, so let's start to look at all these characteristics. Of course, this figure is fancy. Probably you cannot immediately understand in the first sense. But I believe for this one are all the things we have been talking about for many hours. So these are typical IDVG characteristics. These are very typical IDVD characteristics. This is the log scale IDVG characteristic. So the things I want to illustrate that what we have learned from this lecture is pretty useful, because that's already help us to understand the very advanced transistors. This paper is published in the Natural, and then the result here is still considered one of the world record, because they try to fabricate a transistor with only 1 nanometer, like the channel length here. So that's still quite amazing. But the result they exhibit, the figure they show me, is still very typical IDVD, IDVG. That's all. And then the one thing very interesting is this one. If you are really interested in what this paper is talking about, the key point is here. This is a source, this is a drain, and this is MOS2. And they actually try to use this. This is a carbon nanotube. This is carbon nanotube. They use this carbon nanotube as a gate to switch off the transistor. Why do I say the switch off? Because this is, if you look closely, the threshold voltage is negative. So that means this is actually the depletion mode transistor. That's why in the beginning we're talking about depletion mode. Sometimes most of the student will forget that in the MOSFET we still have a depletion mode, but right now you see that the depletion mode still sometimes useful for us. So in this chapter, actually in this literature, is actually the MOS2 is the channel that already conductive. So that means the electron already can free to move in this MOS2. And what we have to do is to find a way to switch off the device, to find a way to turn off the device. So this is a gate. And this gate in here is their channel length here. This is their channel length. And they claim this channel length is 1 nanometer. And so the channel is already turned on. So the only thing have to do is try to prove that the channel can be switched off. So he applies a negative gate. So that's why you can see after the certain moment, after the negative gate, finally the device can be switched off. And it proves that this is a transistor, because a transistor, the main purpose for the transistor is need to be turned on and turned off with a certain gate bias. So below the -3 volt, actually the device can be turned off, and therefore thus this device looks like exactly the same like as a transistor. So that's a main point for this literature here. Okay, so finally we finish the MOSFET. With a certain left time, I would like to continue to move on. There's still some additional concept for the MOSFET that you have to know, especially related to some non-ideal effect here. So the non-ideal phase, the first one is related to what we call the subthreshold conduction. So the subthreshold conduction is the drain current is actually already existing when our gate voltage is smaller than threshold voltage, and this is known as a subthreshold current. So in the previous chapter, we actually always assume the transistor can have the current once the gate voltage is larger than threshold voltage. But reality, it is not true. If you try to plot the log drain current versus the gate bias here, we actually will find out that this is our typical so in the previous we assume this one, but in reality actually the current is already there, and this is experimental result. So the drain current is already existed. If we consider this one is our VTH here, and actually the current is already existed when the bias is smaller than the threshold voltage here. The Fermi level is close to a conduction band than the valence band. This is because right now, even haven't reached to the inversion condition, but your EF here is already close to your conduction band, and which already far away from your valence band here. So therefore, this kind of service is become the lightly doped N-type channel. So it's already kind of like a lightly N-type region here. So therefore, we can expect that let's start have some the electron can be formed. There's a certain some of the electron density in this surface, and the condition which between the 2,5p and larger than 5p is known as a weak inversion. And this one is exactly the same like our CV curve. So everything is very consistent no matter you look at from what kind of aspect here. So in the CV curve, we all know there's also the region is so-called as a weak inversion, which will be here. So this region is a weak inversion, and this region is already the one that we can have the current. And we can also understand from the another point of view by using this band diagram here. So this is a band diagram that will try to plot along these directions here. So first of all, we can look at this figure D. This is a condition where our VG larger than VTH, and therefore you already lower this barrier here, so the electron can start to flow from source to the drain. And this is a condition VG below 0, so the barrier is very high, so you won't be possible to have the electron flow. And this is a condition of the VG smaller than VTH and larger than VG, and that's since the barrier is already reduced, so it's possible electron can start to move from left to the right here. So that is we consider as a substrate hole current. Okay, so if this is some of the equation for the substrate current here, and then this is some of the experimental results that with a different gate bias here, and the next one is what we talk about will be the channel length modulation here. So this is happen when the MOSFET is biased in the saturation region. The depletion region at the drain terminal extend laterally into the channel, and in the end we actually reduce the effective channel length. So as we already see this kind of a graph previously, so once we increase the VDS, actually your channel here is start to moving towards the source side, and therefore this delta L is increased. That means actually your effective channel length now is getting smaller. So this is happens when VDS increase. So right, if your VDS increase, of depletion width increase, and therefore your delta L increase, and then your overall effective channel length is actually decreased. So this is a typical XP, which is describe the region. And then once we consider there's a VDS here, so you have to consider this is a VDS. So the delta L can be calculated by consider this one. In the end, we found out that actually your original current and also with consider the channel length modulation has this kind of a correlation, and where we can have this lambda, and lambda is called the channel length modulation parameter. So that means actually if you try to look at the IDVD curve here, ideally we should have this and saturate, but the problem is now actually the channel length, effective channel length is decreased. Then actually the current is become like in this way. This is because our channel length is decreased, and the reason of the channel length decrease is because our delta L is increased here. So that's the channel length modulation effect. Okay, we will stop here and we'll continue the rest in the next week. So if you have any question, just feel free to let me know. So we will see each other next week.